This circuit is a PWM-fed inverter, which means it converts a DC input into an ACE-like output using pulse width modulation. The DC supply is applied to an H-bridge made using 4 power switches shown here as Q1 to Q4. These switches are controlled by PWM signals generated from a comparator stage. Instead of directly producing a sine wave, the inverter produces high-frequency PWM pulses whose widths vary with time. When observed on the oscilloscope, the red waveform represents the PWM switching pulses, while the blue waveform represents the averaged or filtered effect of these pulses. This is the basic working principle of most modern inverters. The PWM signal controls how long each switch stays on and off during every switching cycle. By changing the duty cycle of the PWM, the effective voltage applied to the load is controlled. The switches are operated in pairs, so that the current direction through the load alternates, creating an AC output. At any time, only 2 switches conduct to avoid short-circuiting the DC supply. The high switching frequency allows smooth control, while the fundamental frequency of the PWM duty variation decides the output AC frequency. This method is efficient because the switches mostly operate in fully on or off states. Although the inverter output looks like a train of pulses, the load and any filter inductance smooth this waveform. The inductor shown in the circuit helps reduce ripple and makes the current more sinusoidal. As seen on the oscilloscope, the blue wave it is formed from PWM pulses. This technique is called sinusoidal PWM and is widely used in UPS systems, solar inverters, motor drives and variable frequency drives. It allows precise control of voltage and frequency with high efficiency and low power loss.